In the last video of this lesson, I'd like to introduce the localized molecular orbital theory that we'll use throughout the semester to connect curved arrows which are drawn on static Lewis structures to molecular orbitals which actually reflect the real distributions of electrons in molecules. The reason we use molecular orbital theory is it brings more information to the table about the spatial positions and energies of electrons within molecules. And in particular, what you'll see is that we can often draw curved arrows that are bogus on orbital or what are called stereoelectronic grounds. We'll see a couple of examples of those moving forward in the semester. For now, I want to focus on showing you what the localized MOs look like and how to translate curved arrows into labels and those labels into orbital drawings that show the interactions of filled and empty orbitals, which are the foundation of both reactivity and resonance. Localized molecular orbital theory makes a direct connection between the component parts of Lewis structures, the bonds and lone pairs, and the molecular orbitals of the compound in question. So the molecular orbitals, which describe where the electrons of the molecule are located in space and what their energies are, then reflect the positions of the bonds and lone pairs, and they're localized in space between either one or two atoms. There are some exceptions to this rule, and we'll cover them primarily in the lesson on pi delocalization, but localized MO theory is a very powerful way to understand the spatial positions and the energies, the stability of electrons within molecules, and electron sinks as well. So how does it work? Well, I've laid down for us the 3 electron sources and electron sinks once again, and each of these corresponds to a particular localized MO. The non-bonding lone pair is perhaps the simplest, and it corresponds just to a lobe that looks like this, encompassing the lone pair with a small lobe of opposite phase on the backside, and this is a hybridized atomic orbital of some sort. In fact, it can be an atomic orbital of any hybridization and any type, sp, sp2, sp3, etc. But the key is that it's localized on the X atom and it has a large lobe where the lone pair is located in space. The pi MO contains density above and below the plane where the 2 top lobes have identical phase and the 2 bottom lobes have identical phase as well. The important point here is that the density is above and below the molecular plane defined by the bond and any of its substituents. The sigma orbital is an orbital of coaxial symmetry that contains a large lobe between the 2 nuclei and smaller lobes of opposite phase on the outside. In large part, the filled MOs reflect intuitive ideas about where we would expect to find electrons in these bonds. For a sigma bond, we would expect the electrons to sit between the nuclei. For a pi bond, we've come to expect that they sit above and below the plane, independent of the sigma bond, which contains electrons in the plane. And for a lone pair, it makes sense that electrons should be localized in a teardrop-shaped portion of space that reflects the hybridization of the atom in question. So these largely make sense, but they convey some interesting ideas. For instance, the pi bond has density above and below the molecular plane, which means that when a pi source is used as an electron donor, the electron acceptor needs to approach either above or below that plane. It can't approach in the plane, otherwise it's going to meet a node. Instead, it needs to come from either above or below in order to receive electrons from the pi bond. What about the electron sinks? What do these look like in orbital terms? The empty A is most commonly just an atomic p orbital located on that central trigonal planar atom. The pi star orbital looks a lot like the pi MO, except that its lobes are phased in an opposite sense, with a node between them. And now with no density between the 2 nuclei, we can see that for an electron source that needs to overlap with the pi star orbital, or needs to donate electrons to this pi star orbital, it needs to come in from one of the edges either to Y or X, and it can't come in the middle. Finally, the sigma star looks quite unique. It's got two small lobes of opposite phase in between the nuclei and large lobes on the outside. And again, intuitively, this makes sense. Remember that the pi star and sigma star localized MOs are anti-bonding MOs, meaning that when they're filled with electrons, they tend to discourage bonding. They do this because there's a node between the nuclei, and the electrons prefer to sit outside of the nuclei. What the sigma star orbital shows us is that an electron source that needs to donate to a sigma star acceptor must do so on the outside edges of the bond. This is most popularly known in the context of the SN2 reaction, where the nucleophile, the electron source, approaches the backside of the carbon-leaving group bond. Notice that approach in the middle cannot take place because only very small lobes sit in that space. What we can see from these orbital pictures is that the localized MOs provide us with insight about the spatial and energetic properties of curved arrows and electron flow. More profoundly, curved arrows represent orbital interactions. So, for example, curved arrows showing the removal of a proton by hydroxide, let's say, from a carboxylic acid, are actually depicting the overlap of a non-bonding lone pair on the hydroxyl group with the sigma star orbital of the oxygen H bond. In the next lesson, what we're going to do is systematize these orbital interactions and talk about the elementary steps of organic chemistry, which are the foundations of all reaction mechanisms. All reaction mechanisms are built from the elementary steps. But understanding the shapes of the localized MOs and how Lewis structures suggest those shapes is a prerequisite to understanding the orbital overlap that we see in the elementary steps. The thing to keep in mind is that the component parts of Lewis structures, bonds and lone pairs, suggest localized MOs, and their shapes are as simple as what you see on this slide.